In late December 1944, a naval aviator's margin was a simple sum: ship speed and wind. When they aligned, the flight deck could feel almost routine. When they didn't, the deck turned into a trap. And for the pilot of the FM-2 Wildcat, Bureau number 57039, it shut in an instant. Today, the aircraft lies in the cold darkness of Lake Michigan at about 200 feet. It is not a complete machine. It is industrial geometry frozen in place, preserved by cold, fresh water and the stillness of the deep, conditions that slow corrosion but never stop it. And to understand what it will take to bring this airframe back, you have to understand the mechanical hazard that destroyed it in the first place. The aircraft is an FM-2 Wildcat, a lighter and more powerful late variant of the Wildcat line, built by the Eastern Aircraft Division of General Motors for operation from smaller decks. However, the deck involved in this loss was not a combat escort carrier. The USS Sable began life as the Great Lakes sidewheel excursion steamer Greater Buffalo, later converted by the Navy into a carrier-qualification training ship. Its side-mounted paddle wheels created a hazard zone unlike the stern-focused risks of a screw-driven ship, danger that could exist alongside the hull, not just behind it. The wreck site confirms the violence of the event without needing any drama added. The aircraft sits in the silt, and the fuselage ends abruptly aft of the cockpit, an overall break that reads like heavy mechanical trauma, not a simple slam into open water. The lake floor suggests a takeoff that never became flight. The airplane drops into the water ahead of a ship that cannot stop on a dime, and the geometry of USS Sable turns that mistake into proximity, wreckage drawn toward the rotating arc of side-mounted paddle wheels. This is the primary constraint of the recovery site. Sable's paddle wheel isn't just background machinery, it's a slow, rotating hazard. As the aircraft went under, buckets and framing designed to bite water met aluminum structure, and the strike did what open water could not. It left the Wildcat as two major sections on the bottom, two independent objects separated by a single, unforgiving rotation. At this depth, the artifact is beyond casual diving and firmly in the realm of technical recovery. Down here, Lake Michigan is cold, dim, and physiologically expensive. Fresh water slows many of the processes that would consume an airframe in warmer, saltier seas, so the shape can remain readable even after 68 years. But preservation doesn't mean wholeness. The story on the bottom is still dominated by one fact. The fuselage is in two sections. Recovery engineers viewing the side scan data see a puzzle. The main body of the aircraft, containing the cockpit, the engine, and the wings, rests inverted or on its side. The tail section lies separately. This separation dictates the entire recovery strategy. You cannot lift the aircraft as a single unit because the structural spine is gone. The recovery team must treat this as two distinct lift operations, each with its own center of gravity and rigging requirements. The objective is clear, but the execution is hazardous. The goal is to retrieve both sections without inducing further collapse. The aircraft is a rare artifact, a survivor of the carrier-qualification program that trained and qualified 17,820 pilots. But right now, it is a compromised structure sitting in the silt. The gap between the cockpit and the tail is the physical manifestation of the accident. It represents the precise moment where the operational timeline of the pilot intersected with the mechanical timeline of the ship. Bridging that gap requires a plan that respects the 68 years of silence and the 200 feet of water pressure pressing down on the aluminum skin. The investigation begins not with why the engine failed, but with how to bring the pieces back to the surface without erasing the story they contain. The decision to abandon a moving aircraft is usually dictated by altitude, but on a carrier deck, it's dictated by the geometry of the ship. Ensign William E. Forbes faced that calculation in late December 1944, cycling through Lake Michigan's carrier-qualification pipeline. The environment was controlled, but the physics of flight remained unforgiving. The aircraft Forbes flew was the FM-2 Wildcat, the last major production Wildcat, and a different animal under the cowling. U.S. Navy Museum specs list a 1,350 horsepower Wright R-1820-65, a meaningful jump over the 1,200 horsepower Pratt and Whitney R-1830 used in the F-4F-4 era. That extra muscle came with handling changes, most visibly a taller vertical tail and related tweaks meant to steady the airplane in the low-speed, high-workload world of small deck work. But on a carrier, you don't get a second set of numbers. When the wind and the ship's run stop adding up, the margin disappears. On what is often described as his third takeoff of the day, the engine provided the initial surge required to start the roll. As the aircraft moved down the wooden flight deck of the USS Sable, the operational margins narrowed. Contemporary summaries describe Sable as a side wheel conversion with a top speed in the high teens, roughly 16 to 18 knots, limiting the wind over deck available on calm days. In carrier aviation, lift is generated by the sum of ship speed into the wind and aircraft acceleration. If one variable drops, the equation for flight fails. Near the bow, reports describe the engine losing power and quitting. The aircraft had not yet reached flying speed. Without enough airspeed to fly, it went off the bow and into the water ahead of the ship. This initiated the lethal sequence that made Sable unlike a screw-driven ship. When an aircraft enters the water ahead of any moving deck, it decelerates brutally, and the ship's forward motion becomes the threat. On Sable, that threat isn't centered at the stern, it lives outboard, where the paddle wheels keep turning as momentum closes the distance on the wreckage. Ensign Forbes had only seconds to act. His decision loop was strictly procedural. He did not attempt to save the airframe. He opened the canopy and got out as quickly as he could after water entry. That discipline likely saved his life. He cleared the wreckage as the port side paddle wheel closed in. The collision mechanics were simple and unforgiving. Paddle wheel buckets, built to bite water, became a rotating battering surface against aluminum structure. Accounts describe the strike as occurring aft of the cockpit, the moment the airframe was cut into two major sections. The main fuselage went under, the tail drifted separately, and Bureau number 57039 disappeared into cold freshwater. The environmental conditions set the stage for what the wreck would become. Engine failure started the chain. Cold freshwater fixed the location. Paddle wheel geometry delivered the cut. What remained on the bottom wasn't a clean crash site, it was a machine separated into evidence. The heavy engine pulled the nose down, the severed tail drifted free, and both sections settled into the silt, waiting for a technology capable of bringing them back without rewriting the story. Finding aluminum on the floor of Lake Michigan isn't a search for color or shape, it's a search for density. At 200 feet, there's no ambient light to work with. So the primary tool is side-scan sonar, sound sent out from a towed fish, returning differently off silt and metal. For the recovery team, the first indication of the FM-2 Wildcat wasn't a camera image, but a hard acoustic return followed by a distinct shadow, blank seabed behind vertical wreckage, sized like a naval aircraft. The sonar data revealed two distinct targets. This geometry confirmed the archival record of the paddle wheel strike. One target corresponded to the main fuselage and wing assembly. The other, smaller target lay nearby, matching the dimensions of the severed tail section. The position of the wreckage was consistent with the known operating area of the USS Sable, but the depth of 200 feet introduced a severe physiological constraint for human verification. At this depth, diver time is limited and tightly planned. The survey has to be disciplined and fast because every minute on the bottom has a cost on the way back up. The diver's not there to sightsee. He is there to verify orientation and condition, just enough to plan a recovery without turning the wreck into debris. When the survey camera finally illuminated the target, it revealed something recoveries from earlier decades rarely had to fight. The aircraft was heavily encrusted with quagga and zebra mussels. Linked to ballast water introductions into the Great Lakes in the late 1980s, zebra first, quagga soon after, they attach to hard surfaces in dense colonies and turn metal into reef. For a forensic recovery, that reef is both mask and burden. It hides markings, bureau numbers, rivet lines, and stress clues under hard shell, and it adds real weight and drag to a structure that hasn't carried itself in 68 years. The survey confirmed the main fuselage was resting inverted. The landing gear was retracted, the wings remained attached despite the violence of the crash. However, the critical attachment points, the lifting lugs, and the spar fittings were buried under inches of hard shell. The recovery engineer cannot simply hook a cable to the wreckage. He must identify a structural hardpoint capable of bearing the load, but he cannot see the metal. This biological layer complicates the standard model of freshwater preservation. In the past, aircraft pulled from these lakes appeared factory fresh. Now they are encapsulated. The mussels do not corrode the metal like saltwater rust, but they hide stress cracks and corrosion pits. The survey team had to rely on the general geometry of the Wildcat to infer where the strength lay. They confirmed the tail was fully separated, requiring a separate rigging plan. They confirmed the cockpit was open, consistent with the pilot's egress. The target was positive. Before recovery, identity could be inferred by location and type. But a bureau number is a bureau number. Confirmation comes only when the markings and structure can actually be read and documented. The challenge shifted from finding the object to moving it. The survey proved the aircraft was there, but it also proved that the aircraft was heavier, more fragile, and more obscured than the clean aluminum time capsules of previous generations. The lift would not just be a battle against gravity, but a battle against the biological weight that had claimed the machine. The engineering challenge of December 7, 2012 was defined by a single structural reality. The aircraft was already broken because the paddlewheel had cut the fuselage decades earlier. The recovery team could not bring the FM-2 Wildcat up as a single cohesive unit. They faced two independent loads, each with its own balance, each vulnerable to twisting and collapse. The risk was that the stress of recovery would finish what the ship had started, tearing weakened aluminum into unrecognizable scrap. They prioritized control over speed. The separated tail came up as its own piece. Then the main fuselage, engine, cockpit, wings, followed, handled in a way meant to distribute forces and avoid crushing fragile structure. The most critical phase of any recovery is the transition zone. And the real cliff-edge moment is the surface. The instant an object breaks the waterline, buoyant support falls away and gravity takes full effect. Trapped water and heavy biofouling don't just add mass, they turn that first breath of air into a sudden, punishing load. To mitigate this risk, the recovery team focused on getting the aircraft into a more controlled environment before final handling on land. The goal was simple: reduce uncontrolled loads and minimize new damage during the move from open water to shore. Water can be both enemy and support. During recovery handling, keeping an artifact supported by water for as long as practical can reduce sudden point loads on thin skins, old rivets, and stressed joints, especially when biofouling adds mass and uncertainty. The same lake that hid the airplane for decades could, for a time, help support it while the team moved toward controlled conditions. Bringing the aircraft into the harbor meant the team could work closer to shore infrastructure and steadier conditions than open lake operations. When the main section finally came clear of the water, the physics changed fast. Trapped water drained, the structure took its first true weight in decades, and conservation priorities suddenly mattered as much as cranes. Out of the lake's cold darkness, exposure to air introduced new risks that demanded immediate care. The evidence brought to the surface on December 7th offered immediate confirmation of how Lake Michigan can preserve wrecks. But the moment an artifact leaves cold water, preservation turns into a race of a different kind. Biofouling and silt begin to dry. Salts, residues, and hidden corrosion mechanisms can change behavior in air. The priority becomes stabilization, keeping the aircraft managed and wet enough, long enough, to document what you have before you start removing what's covering it. As the sprayers blasted away the layers of zebra mussels, the true condition of the artifact emerged. In a saltwater environment, the interaction between aluminum and steel components creates a battery. The salt water acts as an electrolyte, facilitating galvanic corrosion that consumes the airframe in decades. In the deep freshwater of the Great Lakes, this chemical circuit is broken. The water is cold, dark, and lacks the dissolved chlorides that drive rapid oxidation. The absence of light prevents plant growth, and the low oxygen levels at 200 feet slow the degradation of organic materials. The proof of this environment showed up in small, stubborn details. Cold fresh water can leave paint patterns readable and components recognizable long after they would have vanished elsewhere. But every apparent miracle has to be treated as a hypothesis until it's documented, What matters is what can be photographed, measured, and conserved before exposure rewrites the evidence. Further inspection turned to the fuel system, an area where wartime carrier aircraft were designed with survivability in mind. The Wildcat family used protective measures such as self-sealing tanks, but what remained sealed after decades underwater is not a slogan. It is a conservation question answered only by careful documentation as each cavity is accessed and stabilized. The cockpit offered a similar paradox. While the pilot had opened the canopy to escape, the lower sections of the flight deck remained shielded from the sediment. The instruments, the throttle quadrant, and the control stick were coated in silt, but structurally perfect. In places, zinc chromate primer was still visible on interior surfaces, a bright reminder of 1940s manufacturing, muted by silt, time, and the slow work of water. The recovery confirmed that Bureau No. 57039 was not a wreck in the traditional sense. It was a suspended animation of 1940s technology. The damage was limited strictly to the mechanical trauma of the collision. The corruption of time had been halted by the chemistry of the water. The aircraft was now sitting on the dock, separated into its two primary components, dripping wet and smelling of the lake. The easy part was over. The physical recovery had taken a day. The process of reversing the disassembly caused by the USS Sable would take a decade. The timeline of aviation is often defined by speed, but the timeline of restoration is defined by patience. It took only seconds for the paddlewheel of the USS Sable to sever the fuselage of the FM-2 Wildcat. It took 68 years for the lake to hold it in the dark. But the final phase, the return to a displayable condition, demanded a magnitude of effort that eclipsed the aircraft's operational life. AirZoo reporting places the work at over 50,500 volunteer hours. This work was not performed by the Navy, but by a specialized team at the AirZoo in Kalamazoo, Michigan. When the trucks arrived from Waukegan, they delivered a project that was simultaneously robust and fragile. The aluminum skin was intact, but the internal components required total disassembly to arrest the slow chemical changes that begin the moment a waterlogged artifact meets the atmosphere. The freshwater environment had halted the corrosion, but it had not suspended the need for conservation. Every rivet, every spar, and every bracket required inspection. The central engineering challenge of the restoration mirrored the central trauma of the crash. The aircraft arrived in two primary pieces. The tail section had been violently separated from the fuselage. Reconnecting these sections was not a matter of simply bolting them back together. The metal had been sheared, torn, and deformed by the impact of the iron paddle blades. The restoration team had to reconstruct the structural continuity of the airframe. This involved straightening bent longerons and fabricating splice plates that could bridge the gap created in 1944. The process is slow because it is forensic. Modern restoration standards do not favor erasing the history of the object. The goal was not to build a new airplane, but to save the one that Ensign Forbes flew, retaining as much original material as possible. The hours went into toothbrush work and mild solvents, into careful handling instead of replacement, into preservation rather than production. This specific airframe now serves as a tangible anchor for a much larger statistical reality. Between 1942 and 1945, the Navy qualified 17,820 pilots on the Great Lakes paddlewheel training carriers. These men flew in an environment unique in naval history, carrier work on inland freshwater, often in bitter weather. On ships converted from civilian steamers, they learned the geometry of carrier aviation before deploying to the wider war. Most of the aircraft that failed during this process were lost to the scrap drives of the post-war era or remain hidden in the silt. Bureau No. 57039 is a rare exception. It is a survivor of the hazard inherent in that training model. The aircraft does not just represent the engineering of General Motors or the tactical needs of the war. It represents the calculated risk taken by 17,000 individuals who accepted the constraints of the flight deck. The project concluded with the aircraft finished in an Atlantic tricolor scheme associated with U.S. Navy Wildcats of the era. It stands today not as a monument to tragedy, but as a record of a specific technical moment. Engine cleaned, cockpit stabilized, a severed tail reunited with its fuselage. The water is gone, and the story is now protected by museum climate control rather than the depth of the lake. Air Zoo reporting notes the completed FM-2 Wildcat as a centerpiece on display at the American Heritage Museum in Hudson, Massachusetts. The loop that began with a loss of power on a cold December morning is finally closed.